Good morning or good afternoon, everybody. This is Carl Pilcher at NAI Central, and it is my pleasure to be welcoming you to and introducing the speakers for the second director seminar of this series. One of the things that is really exciting about astrobiology to me is how it attracts many young researchers beginning their careers. And I think that's a testament to how exciting the field is. And both of the first two director seminars of this series are being given by young researchers. Today's seminar is being given by Raymond and Avi Mandell. They have been researching the formation of habitable planets around other stars and have come up with a very interesting conclusion to a fundamental question, namely, can there be habitable planets around stars that also have giant planets close in? And they're going to be telling us about their work. Raymond is an NAI postdoc at the University of Colorado, who got his PhD at the University of Washington in Seattle under Tom Quinn and is working now with John Bally at Colorado. Avi Mandell is, in fact, still a graduate student. He got his undergraduate degree at Vassar College, and he's a graduate student at Penn State, working with Stein Sigurdsson and John G. Their research, in both cases, focuses on the formation and evolution of habitable planets. And today they're going to be telling us about the formation of habitable planetary systems, and they're going to provide an answer, I guess, to the question, are we normal? So I turn it over to Sean and Avi.
All right, I think I'm up first. So hello everyone in this room who is kind of thinking this is weird since I'm sitting down the whole time. But that's because we want people who are not in this room to be able to see my face. So I can't move further than about this far on either side. So and hello everyone who's not here. So I'm Sean, and I'm going to be telling you guys a little bit of the background of this problem. And then Avi is going to tell you about the exciting new stuff we've been doing. And so to start it off, we've created this kind of sexy picture right here, which is showing 4 different planetary systems. And so the one on the bottom right, hopefully you'll recognize as a very rough schematic of the solar system. Nothing is even close to scale, but you get the general idea. You got Mercury, Venus, Earth, and Mars in there. Earth is in this sweet spot in what we call the habitable zone. I'll talk more about that in a minute. Got an asteroid belt, got Jupiter, and there's more stuff further out. And this is just showing the inner planetary system. These other 3 planetary systems I'm showing are artificial ones that were created in a computer, and we think they're reasonable representations of what might be out there and might be discovered in the next 5, 10, 20 years or so. So on the top right is a system that includes a planet that looks a lot like the Earth. Its orbit and composition and size are similar to the Earth's, but the system as a whole looks a lot different. The only giant planet in this simulation is only about the size of Neptune rather than being the size of Jupiter. And so in the end, instead of forming a relatively small number of terrestrial planets, we formed about 6 or 7 terrestrial planets in there, several of which are kind of Mars-sized. In the top left is a system that includes a planet in the habitable zone as well. That's this weird red one right there. And the weird thing here is that a planet formed in the habitable zone, which is at the right temperature for water to be liquid on a planet's surface. But it turns out that planet was unlucky in some sense and actually doesn't have any water on it. So it's in this weird state of being in the right place to have water, or water as a liquid, but it's got no water on it. So that's kind of unfortunate. And the bottom left is a system that looks a lot different than our solar system. Remember, nothing's even close to scale here. So this is a hot Jupiter right there. Even closer to the star is what we call like a hot Earth or a hot super-Earth planet, a planet a few times the mass of the Earth that's within 0.1 AU of the star. And out here is a planet on an orbit similar to the Earth's. It's in the habitable zone. It's got roughly similar properties to the Earth. The only difference is that this planet has maybe 10 or 20 times as much water as the Earth does. And so it's probably covered in deep oceans. All right, so moving on. Here's a list of collaborators who have helped on this project, notably Tom Quinn and Stein and Jonathan Lunine. Those guys have helped a lot. And we want to thank NASA Astrobiology for funding. Personally, I've been funded through them for the last 4 years or so at the University of Washington, then at the Virtual Planetary Lab based in Caltech, and then now at the University of Colorado. And Avi is also supported at Penn State and NASA Goddard. So here's an outline of what we're going to talk about. I'll give a brief overview of the general picture we have of how the solar system planets formed. I'll go into a little bit about what I'm talking about a habitable planet. Then we'll look at planetary systems that are similar to our own, in that if they have giant planets, they're exterior to the terrestrial planet region. Then planetary systems unlike our own, which have giant planet systems which are either interior or probably interior to the habitable zone. Then we'll look at the known set of extrasolar planets, and then conclusions that are typical in these kind of talks. So I'm going to do things a little bit backwards. Here at the very start is the punchline. So this plot is highly confusing to everyone I ever show it to. So let me just explain it very briefly, and Avi will explain it in more detail in a little bit. So what we're looking at is a plot of a giant planet orbital distance as a function of stellar mass. And this shaded region is the habitable zone. And each of these dots on here represents one of the known giant planets. The solid and dashed lines are limits, which we've derived in a way that we'll tell you about later, for where giant planets can be, basically orbital limits for giant planets that allow terrestrial planets to form in the right place, that we think maybe liquid water could be on the surface, maybe life. And so if you go out and find a new giant planet, you can stick it on this plot, assuming you've measured its orbit and the mass of the star that it's around. If that giant planet falls above the solid line or below the dashed line, and also has certain other properties which are not shown explicitly in the plot, like its orbital eccentricity is below a certain limit, then that system has a good chance that a terrestrial planet could have formed in the habitable zone. So I know that's kind of a long and convoluted sentence, and Avi will clarify that much more later, so that's nice. Okay, so getting back to this idea of terrestrial planet formation, we only know in detail of one planetary system, the solar system. Here's the new solar system planets. We only have 8 of them now. Some people are sad about it, but I don't really mind. Anyhow, so the solar system gives us constraints. We have models for how planets form, and they have to match more or less the solar system, because that's the one system we know in detail. We have to match things like the mass of planets. We have to match the orbits of planets, their compositions, their rough spacing, isotopic ratios, populations of small bodies like asteroids and comets. So that's kind of our baseline. Hopefully we have a theory that can more or less reproduce the solar system. And what we're going to do is we're going to take that general picture that works for the solar system and apply it to other planetary systems. And hopefully we'll learn something by doing that. So now I'm going to be talking, the rest of the talk is going to deal a lot with habitable planets. And so what is a habitable planet? Obviously, it's a planet that has the possibility of having life on it. So what do you need? What requirements are there for a planet to maybe be habitable? And so it's been proposed maybe you need a thick atmosphere. If you need a thick atmosphere, then your planet has to be big enough to have enough gravity to be able to retain an atmosphere of that size at the right orbital distance. And that turns out to be, a planet has to be at least about the size of Mars, about 1/10 of an Earth mass or so. Some people have argued that plate tectonics is key for long-term climate stability on a planet. So if that's a requirement for habitability, then the planet needs to be bigger than maybe 2/10 of an Earth mass or so. And then if we kind of fiddle with the parameters there and say a planet has to have plate tectonics that lasts at least some amount of time, maybe 5 billion years, assuming it has a density of something like 4.5 grams per centimeter cubed, then you get a rough limit on what mass of a planet that could have those properties is about 1/3 of an Earth mass or so, 0.3 Earth masses. And so that's the rough cutoff we're going to use. We're going to say that planets below that mass have a smaller chance of being habitable. And maybe in some instances they are habitable, but we're going to use that as a rough dividing line between smaller, less habitable planets and more massive habitable ones. And so this plot here shows a schematic of what the surfaces of 3 different planets might look like, all in the habitable zone. And so the one on the left is showing maybe a Mars-sized object, and maybe this thing would end up being dry and and desert-like Mars. Then we have the Goldilocks planet where everything is nice and happy, which is where we live. And maybe larger planets would end up having a lot of water on them. And I'm not sure I agree with this theory, but it's kind of a nice picture of what surface of these planets might look like. So you've heard all about the habitable zone, and I'm sure most of you know what it is, but let me just give you a very quick reminder. So it's the region of orbital distances from a star where the temperature is right on the surface of a planet that water can be liquid. And of course that depends on things like the planet's atmosphere and such. And there could also be habitable niches where you have another source of heat. For example, Europa might be habitable given that it has a different source of heat rather than solar irradiation. But this is a very simple way to define it. If your heat's coming from the sun, then you have to be in this range of distances to have liquid water on your surface. But the trick is not only do you have to be in the right spot, but you also have to actually have liquid water on the surface of the planet. And so this right here is the universal symbol of planetary habitability. So that's what life likes beer. Okay. So the general stages in how terrestrial planets form goes something like this. And this picture kind of illustrates this image illustrates the rough model that we think we understand, more or less. So there's several different stages. First, as planets are forming in this disk of gas and dust around a star, grains kind of settle to a midplane, a very thin midplane of, in this disk around the star. That takes something like 10,000 years or so. Step 2 in this problem is very uncertain. There's lots of hand waving in terms of how you get from small grains to kilometer-sized planetesimals. We think that kilometer-sized planetesimals are really the building blocks of terrestrial planets, and so we think that they have to form somehow. And exactly how they form is not really well understood yet. The third stage of terrestrial planet formation deals with the agglomeration of kilometer-sized planetesimals into maybe moon-sized protoplanets, or they're also called planetary embryos. And the final accumulation of terrestrial planets is called late-stage accretion, and that occurs in maybe 10, 50, 100 million years or so. And a key thing to note here is that giant planets are required to form faster than a few million years. So the final assembly of terrestrial planets takes place in the presence of any giant planets which may have formed. And they don't have to form around every star, but in the cases where you do have giant planets, the final accumulation of terrestrial planets is influenced by those giant planets. So what does this disk of gas and dust look like from which the terrestrial planets form? Well, one key thing is that close to the star it's hotter. When it's hotter, then you can have, different materials that are able to condense. And so it's thought that close to the star, what dominates the solid bodies are rock and iron. Further away, it's more volatile materials that dominate, like water. And when you get very far away, things like carbon dioxide, methane, and so on. And one way that we think this is the case is by looking at classes of primitive asteroids, right? Looking at meteorites, which we think originated in families of asteroids which are supposedly representative of the conditions that where they formed. And so if you look at those, that's this plot on the left here showing the water content of those bodies as a function of orbital distance. And kind of fitting this general picture more or less, bodies that are further away from the sun have more water, ones that are closer have less. And so carbonaceous chondrite meteorites, which originate in C-type asteroids at maybe 2.5 to 3.2 AU or so, those have maybe 5 to 10% water in them. And so one interesting thing in terms of forming these habitable planets is, I mentioned, like on the Earth, for water to be liquid on the surface of the Earth, it's got to be hotter than 0 degrees Celsius. Okay. The trick is, how do you get water onto a planet? The current thinking is that the only way you can really do this in large quantities is by accumulation of ice. And so it's going to be in the form of icy material that ends up on the planet. So that means that you have to have some ice forming. And in the low-density environment of this protoplanetary disk, it turns out that ice only condenses into a solid when it's colder than about negative 100 degrees Celsius. So your habitable planet has to be hotter than 0 degrees Celsius and colder than negative 100 degrees Celsius at the same time. Right? That doesn't sound right, does it? So that's kind of this we call a catch-22 of habitable planet formation. And the solution to this is, oops. Oh, anyhow, I think we must have removed that slide. So the solution to this is a planet that forms at the right temperature to have water on its surface, one where it's hotter than 0 degrees Celsius, must have incorporated some material which originated further out in the disk. So it has to incorporate some material from out at a few AU at least, in order to, even though it incorporates this material, it still lies at the right temperature at 1 AU or so. So that's the general solution to this problem, that even though planets that end up in the habitable zone are at the right temperature, they can't form only from local material, because that local material is probably dry. So putting all these pieces together has been done over the last 10 or 20 years, or actually more like 50 years or so. And the general picture looks pretty good. This plot here is very hard to see. It didn't transfer very well, but what it's showing is from simulations by an Agnor paper in '99. It's showing the mass of those planets that formed in these simulations as a function of orbital distance. And these squares that you can kind of just roughly make out here are the terrestrial planets. And these other symbols are planets they formed artificially in their computers. And if you kind of squint it, it looks like you can make yourself believe that the terrestrial planets fall in this distribution, and that we're just kind of, somewhat, in a normal distribution of planets, we're just a high likelihood outcome. The trick is these simulations are not as realistic as they would like to be, because in any given simulation, they didn't form 4 planets that look like Mercury, Venus, Earth, and Mars. They typically formed only 2 terrestrial planets. But then if they plot them all on the same graph, it looks kind of nice. So this is not the final answer on the thing, but it's a step in the right direction. And there's new simulations which do reproduce the terrestrial planets much better. And so in general, these models can reproduce the masses and the orbits of the Mercury, Venus, Earth, Mars pretty well, starting from only these simulations here that in this plot only started from 30 to 50 particles, planetary embryo particles. And so they do a pretty good job of doing that. We can explain the source of water on the Earth as coming from C-type asteroid-like material, stuff that originated maybe 3 AU or so. There's a few big problems with this, with the model so far. The first one is the key. There's no good explanation for Mars. For every disk, model disk, for every simulation that's out there, no one's formed Mars that's small enough, doing this properly. And so that's kind of a big issue that's still unexplained. And there's a couple little issues that they're still, remain to be solved. But the general picture looks pretty good. So we have a decent model that can explain how our solar system terrestrial planets formed. And so now we're going to do that part where we look at, try to apply this to other planetary systems. Okay, so what we're going to do here is look at computer simulations of how planets form. We're going to look mostly at that stage 4 from a few slides ago, the final stage of terrestrial planet formation. And so what do our initial conditions look like? In reality, we think that there's probably a few hundred of these moon-sized planetary embryos out there, and they're embedded in a swarm of trillions of kilometer-sized planetesimals. And we're also assuming that giant planets have formed by this time of the final agglomeration of terrestrial planets. Any giant planets have already formed. So that's kind of reality. We think that's what things are really like. The trick is you can't simulate trillions of particles, at least not at the moment, because our computers are too slow. Or maybe we're too dumb. I'm not sure. But anyhow, we can't do that. So we're using these approximations where we use maybe up to a couple thousand initial particles, maybe 10 to 20 Earth masses, and we change the water content of bodies based on how close they are to the sun from that graph I showed you a few minutes ago. And I think I'm actually going too slow, so I'm going to speed up a bit. But anyhow, this plot here is showing kind of a typical set of initial conditions. These bodies here, which are really not too easy to see, these are planetary embryos in the disk of planetesimals, which are these guys. And the water content goes from very small to much larger further out. That's a typical set of initial conditions. And here is a typical simulation. This is a simulation with one giant planet, which is meant to be a rough representation of Jupiter, at 5.5 AU. And so each of these is showing snapshots in time of particles. It's showing the eccentricity of each particle which has survived in the simulation as a function of its orbital distance. The color of each body represents its water content. Red means that they're dry. Blue is 5% water in this case. And so this is kind of snapshots in time of one of these simulations. So what happens? Within 100,000 years or so, bodies are getting some eccentricities. In the inner disk, eccentricities come from scattering among protoplanets. In the outer disk, that eccentricity comes from interactions with a giant planet, which is just off the picture here. So these vertical spikes are mean motion resonances with the giant planet. When these bodies get eccentricities, that means the range of orbital distance over an orbit, basically the range of distances from the star over an orbit changes, so the orbits can cross. You can have collisions, and you can see bodies are starting to grow, kind of from the inside out. All the timescales are shorter, closer to the star, so these things happen much faster, close to the star. They form from the inside out. After 10 million years, this guy right here is almost the mass of the Earth. But you'll notice that its orbit is pretty close to the Earth's orbit. It's about 1 AU, but it's completely dry. But still, you have all this material, all this blue material, which is on all sorts of chaotic orbits at this time. Over the last, few hundred million years of the simulation, all that material gets swept up. Some of it gets chucked out by Jupiter. Some of it ends up on terrestrial planets. And in the end of this one, this guy right here is about 2 times the mass of the Earth. Its orbit is quite similar to the Earth's. Its eccentricity is a little bit bigger. But it accumulated a good amount of water, and it's a decent representation of the Earth. Out here we have some asteroid particles which hung around too. So this is kind of what a typical simulation looks like in terms of what goes on during the simulation. Oh, I'm going to skip this one because I think I don't have enough time. This is just showing some of the details of what happened in that given simulation. An interesting thing that happens is I mentioned before, the giant planets are really affecting what's happening in this final stage of terrestrial planet formation. And one thing that's been noticed among the known giant planets is lots of them have relatively large orbital eccentricities. And so how does that affect the terrestrial planets? Well, if you have one giant planet on the same orbit as Jupiter, and all you do is change its orbital eccentricity, it really affects the terrestrial planets. And so what each of these panels is showing is the final configuration of a given simulation. The 3 on the left have a Jupiter-sized giant planet on a circular orbit. These guys all have giant planet with an eccentricity of 0.1, and here 0.2. And so the punchline is, all these terrestrial planets look nice and green or blue. They got lots of water. More red, more red. So what's happening is the eccentricity of the giant planet is basically exciting that water-rich material in the outer, kind of in the asteroid region, is chucking it out before it gets a chance to move in and end up on the terrestrial planets. And in addition to these kind of systematic trends that I'll talk more about in a sec, there's a lot of diversity in terms of the planets that can form in these simulations. So this is the final configuration of 11 simulations that formed a planet on an orbit very similar to the Earth's. So each of these simulations has a planet that formed between 0.9 and 1.1 AU. And so you notice that the planets themselves, these habitable planets themselves, have a range in what they can look like. The Earth is shown, the solar system is shown in the bottom right for scale. So sometimes there are these humongous water planets which have, this guy here is about 4 Earth masses and it has a ton of water on it. Whereas this one here is one I showed earlier. It's a little smaller than the Earth and it has no water. It got unlucky in some sense. And notice also that the systems of planets themselves have a large diversity. This top right one has just one terrestrial planet that survived, whereas this one down here has a whole load of smaller planets which hung around. And the differences there can probably be explained by the giant planets. In this top right one, the giant planet was 3 times as massive as Jupiter, so it cleared out that material much more effectively than Jupiter. In this case down here, the only giant planet was about the size of Neptune, and so it didn't end up clearing out too much, and so there's lots of crud floating around in the end. And so this is back to that initial plot. This is a rough, completely not to scale representation of some of those simulations I just showed you. Here's the solar system for scale, and then here's kind of a very rough picture of some of the possible outcomes. And kind of this diversity in the systems of planets that can form comes from two sources. One of them is very simple. It's just what's called the stochastic nature of the accretion process. And why is it stochastic? It's because, as I mentioned, there's only a few hundred, or maybe even less, of these protoplanets, these planetary embryos, which are the building blocks of terrestrial planets. And so there's lots of noise in terms of what can happen. If it was, basically, it's because of small number statistics that you can have a large range of outcomes. But there's also systematic variations, which depend on the giant planets, for example. As I mentioned before, a higher eccentricity of giant planets can affect terrestrial planet formation as well as the mass. And in addition, the key one is the disk of material from which these planets form. Both the total amount of mass in the disk as well as the density profile of the disk are very important. So, for example, a more massive disk stirs up bodies more. Bodies have larger eccentricities. What does that mean? That means that over a given orbit, a planet is going over a wider range of distances from the star. What that does is it makes the feeding zone of that planet a little wider. It makes that planet more massive because it's sampling more material. It has more material from which to grow. But it also means that you're going to have fewer planets because you can't stack as many of these feeding zones in a given zone. So I think that's where I'm transferring over. So that's the end of my part. And I'm going to pass it to Avi now, who should be showing up on our TV screen any moment. So Marco, can you pass the thing to Avi, please?
Yes, it's passed.
All right. Can everyone hear me? I hope so. We're now going to be talking about the next phase of the different types of systems that we can examine, which are systems that don't look very similar to our own solar system. And as Sean said, with small number statistics and a very chaotic formation process, there's lots of ways that a system can look different than our own solar system. But we're going to discuss a line of research that we've taken recently that specifically explores systems similar to the extrasolar planetary systems that we've recently discovered in the last 10 years or so. Now, most people know by this point that most of the systems found outside our solar system are systems including a close-in giant planet. And this is a planet which is very close to its parent star. Do I have control here? Nope. Oh, there it is. Okay. Systems where a giant planet is very close to its parent star, and that through theory and also observation of different systems that are forming and theory simulations that we've done in different types of situations, we now realize that those planets probably formed out where Jupiter has formed in our system and migrate inwards through the inner system and then park themselves very close to the star so that they pass through the habitable zone where a habitable planet might be forming at the time and then end up removed from the terrestrial planet zone. And so one of the natural questions that you have in this situation is, can habitable terrestrial planets form in systems where giant planets migrate? And this is the most obvious question when it comes to systems very different from our own, because these systems have a giant planet in the very interior part of the system and may or may not have a giant planet in the outer part of the system. And so previous ideas, well, most people who previously discussed these questions really made pure assumptions based on ideas about planet formation and about the formation of these systems that were mostly based on speculation. Several different groups suggested that the migration of a giant planet would completely vacuum up or evacuate through scattering the interior region in the system, and they would have no terrestrial planets left over after a giant planet had migrated through. Some groups even speculated that this would cause the majority of extrasolar planetary systems to not contain any terrestrial planets, and that this would make the possibility of life on other planets and other systems a rare event. And if you sort of moved forward through time, people began actually investigating this question, and the first group suggested that nothing would be able to form post-migration in a system, but these same simulations made the same assumption as earlier researchers, suggesting that nothing would survive the migration, and therefore post-migration, not enough material would be left over to continue forming planets. However, in 2003 and 2004, researchers began making models and simulations that actually began testing this hypothesis of whether material could survive migration in different types of systems. And several groups showed that much of the material survived migration. Of course, that depended on various parameters, such as the migration rate, the size of the objects once as migration occurred, the size of the giant planet. Just as similar simulations had shown in systems like our own, the systems were fine-tuned depending on the parameters, and the survival rates followed these fine-tuning parameters. And then another simulation in 2005 by Sean and others looked actually at post-migration formation and basically assumed that all material does survive, taking the opposite assumption of earlier research, and actually looked at the formation process in the presence of a giant planet very close to the star, and showed in that scenario that you could have terrestrial planets form on the outside of giant planets in close orbits. Of course, if you look at this whole list, you have various assumptions that need to be tied together in a complete formation simulation, and we decided to do that in our work last year. So we had to include a couple new processes that had been found to be important and in systems that were forming very early. And if you think about giant planet migration has to occur in the presence of a gas disk, because type 2 migration, which is the name for giant planet migration in the literature, relies on the torques from the gas disk and the locking of the giant planet into this gas disk, that then as the gas disk falls onto the inward star, this inner star, the giant planet is forced inward to a small orbital distance. And this is only effective, simulations have shown, for gap opening bodies, which are bodies that have masses more than the mass of Jupiter. Of course, that can be modified depending on the disk mass or other parameters, but the basic idea is that only fully formed giant planets that are a certain size can open a gap and therefore undergo type 2 migration. But the key is that the first parts of terrestrial planet formation and giant planet formation and migration therefore occur in the presence of the gas disk. And so aerodynamic gas drag on small planetesimals and larger bodies is an important factor in this part of this stage of terrestrial and giant planet formation. So we had to take these different processes into account when we are actually simulating the formation of planets in these circumstances. And so we put these different processes into the code, similar codes that Sean and I had used in previous research to study formation of planets in the later stages, and we looked at the formation of terrestrial planets in the presence of migration of a giant planet. Now this is a plot, it's a bit complicated, but it's a basic plot showing from top to bottom the evolutionary steps through the migration and subsequent evolution of a planetary system, where the giant planet, you can see the giant planet is the large black object here, and as Sean mentioned in previous plots, the color scheme refers to the bottom color bar, which is the water mass fraction, with the inner bodies that are red having less water content, and the outer bodies, which are dark blue, having much higher water contents. And so the Jupiter mass planet here in the top starts out at 5 AU, where Jupiter formed in our own system, or similar, near to the location where Jupiter formed. And then over 100,000 years, which is basically falls in between this line here, Jupiter migrates in to about 0.25 AU, migrating through the interior region, and then stops due to various processes which we could talk about in more detail, stops in the inner system and remains there for the remainder of the simulations. Now you see a lot of the same phenomena that Sean had mentioned in his previous simulations, where these resonance reactions, eccentricity, which is on the left here, this is eccentricity, and on the bottom is distance, semi-major axis. Eccentricity is pumped up within resonances, and bodies are scattered to the outer system. You can see in this this third box that bodies end up with a characteristic arc. Yeah. Okay. Sure. Let me set up the laser pointer.
Yes.
Okay. Okay, I hope you guys can see better now as I point to this box. This third box here with the characteristic arc of bodies that eccentricity increases with semi-major axis is characteristic of scattered bodies, where a large body scatters the inner bodies out to further distances. But what is noted here is that a large percentage of the mass actually remains in the system, either through low energy scattering events, which are these bodies here, or higher energy scattering events that end up with highly eccentric yet gravitationally locked orbits within the system. And what occurs over the next 200 million years is that the system continues to evolve after the giant planet has removed itself from the rest of the system, from gravitational interactions with the rest of the system. You can see what happens is a migration of water-rich material occurs through the interaction of small bodies with the gaseous disk over the remainder of the 10 million years. This is the 10 million year box here, down here, and you can see that a lot of the water-rich material, the smaller bodies, are migrating inwards over time. The other thing that occurs is a damping of the system through gas drag, and you can see that bodies that were at high eccentricities and inclination, which is not shown here, inclination is shown with the error bars on each body here. These are not error bars in the actual information plotted, but actually in the inclination of each body. And so the inclination and eccentricity has been damped here. Now, after 10 million years, the gas disk has disappeared, has dissipated from the system, and the remainder of the evolution occurs without the presence of gas drag. And what you see is that remaining bodies in the outer system especially are pumped up in eccentricity and inclination. And this occurs after the damping force from the gas has disappeared, and this increases accretion in the end, the later stages of formation, and clears out the system so that after 200 million years you have, in this case, one planet left in the habitable zone, and evolution of the system continues at a slower rate in the outer part of the system, so you have bodies remaining that are continuing to evolve dynamically compared to the inner system. And this is similar to what Sean skipped over quickly, which is just accretion trends over time. And you can see that for a body called a hot Earth, which I'm going to go back one step to the previous, you can see that hot Earths are these bodies that form in the inside of the migrating giant planet. Now what happens is that material gets caught in a resonance with the giant planet as it moves in. And this is aided by the forces of gas drag, which damps down the eccentricity and minimizes scattering of the material inside of the giant planet. And what ends up is you result in a super Earth mass object interior to the giant planet. It's often usually has a water content that is a mean or so of the material within the giant planet, and it's stable on relatively long time scales depending on the damping forces in the system, and that can be explored more at later times. But what you can see is that the hot Earth receives most of its material right near the end of migration. Migration ends here at 10 to the 5th years, while the bodies outside of the hot Earth, which are these outer terrestrials at 1 AU and around 3 AU, receive most of their material at later times as the gas dissipates. The gas disk disappears completely at 10 to the 7 years, and the material begins to accrete at a faster rate once bodies are dynamically enhanced, that their eccentricities and inclinations are dynamically enhanced. However, this is the water content. Here you can see the water mass fraction. Most of the bodies receive most of their water at the end of migration, this is when most of the scattering occurs and most of the radial mixing in the system occurs here. Now what happens here at the end of the gas disk is that material has migrated inwards, and as their eccentricities and inclinations increase, the accretion of water-rich material occurs more rapidly for the outer terrestrial planets. So this just demonstrates a couple of the interesting facets of this different formation scenario for different types of systems. I'm going to quickly go over the remainder of the slides here. This is just a layout of the giant interior giant super Earths, hot Earths, inside the orbit of the giant planet. These are for 8 different simulations, which included gas drag in them. And I'll explain the different types of simulations later. But you can see that here at the top are listed the resonances with the giant planet, or average resonances, considering that the planet is at a slightly different orbital position. But you can see that what happens is that the super Earth type bodies line up similar to the resonances, close to the resonances with the giant planet. And multiple bodies can exist at the end of migration in different resonances. Slightly interior due to their own migration due to gas drag, but close to the resonance position with the giant planet. The problem is that once gas disappears and the dissipating effect of small bodies, as you can see here, diminishes, these bodies can become unstable due to their close proximity to the central star and to the giant planet. And this is something to be explored further in other simulations, the stability of these bodies. But this demonstrates that hot Earths can form through migration of the giant planet, and these bodies have actually been discovered around several stars recently in extrasolar planetary systems. Now this slide shows the outcome of all 12 simulations with giant planet migration, and they include different parameters for the initial conditions of the simulations. The top 4 simulations have no gas drag, while the bottom 2 simulations do include gas drag from the outer disk. These top simulations were performed mostly as an endpoint limitation on the effects of gas drag to explore how a system with no gas in it might evolve over the full lifetime of the system, and to be able to compare with the other 2 simulations. The other 2 simulations, the one in the middle, the second one here, includes both Jupiter and Saturn. You can see a Jupiter mass body has migrated inwards, while a Saturn mass body remains in the outer system. And this includes no Saturn mass body in the outer part of the system, and only one giant planet, a Jupiter mass body, that has migrated in. And you can see in all simulations, even the simulations without any gas drag, no presence of a gas disk, you can see that close to Earth mass objects, or in many cases multi-Earth mass objects, exist in the habitable zone of these different systems. On the bottom here you see a schematic of the solar system with Earth, Venus, and Mars, and the habitable zone between 0.8 and 1.5 AU is listed. And the systems, several of them have not finished evolving. You can see this JD5 has most likely cleared out most bodies in the inner system, while other systems continue to evolve over the next several billion years. It would take much longer than these simulations have been integrated for to fully explore the evolution of the outer system. But you can see that very water-rich bodies form. And this is due to the migration of water-rich material and the radial mixing from the migration that occurs. And bodies are much less water-rich when you don't include gas drag. That's naturally due to the lack of migrating smaller bodies from the outer system, which are water-rich, and contribute to the water fraction in the inner system. So this is an artist's rendition of one of these water-rich planets. You can see that the planet would most likely be covered completely by global oceans. That's due to the fact that the water mass fraction is almost a tenth of the solid material, the rest of the solid material on the planet. And therefore, since the density is lower for water, most of it would be on the outer parts of the planet, and you would have vast oceans. And we can have a little fun and talk about biological evolution and possible large biological organisms that might grow in these systems, but we'll leave that till later. But the more important factor is what might we be able to tell about known extrasolar planets in other systems. And this is just a schematic various different ways of representing extrasolar planetary systems that have been discovered in the last 10 years. This plot on the lower left shows semi-major axis, the distance, with eccentricity of 168 planets known around other stars, and you can see that a large fraction of the systems have planets very close to their parent star, within 0.1 AU of their parent star. And systems farther out may have very large eccentricities or very low eccentricities. It's unclear what drives the full range of eccentricities in these systems. We have not yet begun to explore the region out past 5 AU where Jupiter currently exists. And that's hopefully going to bring a whole new phase of planetary exploration in the next 10 years or so. You can see the systems are very different from our inner solar system. You can see the Upsilon Andromeda system has 3 massive planets within the range that our own inner solar system. And so these systems can be very different in the size and orientation of these planets, of these systems. So I'm going to move on. As Sean mentioned, you can take these simulations that we've produced of planets that have migrated to their inner part of the system, and you can try to come up with a limit for how terrestrial planets might form in systems of different giant planet orientation. Now, if you look at this, I'm going to skip through to be able to get some of the lines that are drawn on here. If you look at the inner giant planets, you can see that within a proximity to they have a close proximity to terrestrial planets that are formed outside of these giant planets. However, it's at minimum a factor of 9 in orbital period from the closest terrestrial planet formed to the giant planet. In each system formed here, out of all of these 8 systems, the closest proximity of a terrestrial planet to a giant planet is about a factor of 9 in orbital period. And if you expand this outwards, basically, to look at the closest proximity that a giant planet could be to a terrestrial planet that forms in the habitable zone, you end up with a closest approach of about 0.5 AU. If you moved one of these giant planets to about 0.5 AU, then you would have a terrestrial planet forming at the outer edge of the habitable zone. Now, if you get a similar result from Raymond et al. 2005 and 2006, this gives an outer limit of about 2.5 AU for outer giant planets. And then you end up with a plot that looks the plot that Sean showed at the beginning of the talk, which gives limits on known extrasolar planetary systems based on the proximity of a terrestrial planet forming in relation to the giant planet. And so it can be shown that about a third of known exoplanet systems could have formed a habitable planet in known exosystems in the habitable zone compared to the giant planets. Now this, as Sean said, assumes certain parameters. The giant planet has to have a low eccentricity, and it's unclear what the scaling with disk mass would be. If you have large stellar masses, would the disk mass be larger, and would that change the formation and the proximity of formation to the giant planets? But this is a first attempt at creating what could be known as a habitable formation zone in known exoplanet systems. So if you look again at the diversity of habitable planetary systems, you can look at the solar system, you can look at a giant planet, which is only 10 Earth masses, and you form planetary habitable planets in different formations, possibly more habitable planets and more water-rich planets. If you could have a Saturn mass planet, which forms possibly super Earths, which are very water-rich, and then you can form systems with a Jupiter mass planet interior to the system at small distances, and they have possibly very water-rich planets, as well as hot Earths in this hot Jupiter system. So quickly moving through this slide, when are we going to find terrestrial planets around other stars? There's a number of missions that are going up within the next 10 years. Corot actually goes up hopefully by the end of this year in 2006, and we'll be able to detect 2 to 3 Earth mass planets in the habitable zone of systems like this. Kepler will hopefully go up in 2009. and we'll detect many more Earth-like planets, possibly 50 terrestrial planets. And then these other missions are further delayed, but we'll have much greater chance to find Earth-like planets in the habitable zone and possibly detect the spectra of terrestrial planets to figure out what the water content is and possibly what the possibility of life is on those planets. Conclusions. Very similar to the ones we've mentioned multiple times, habitable planets like our own can form in a diverse range of planetary systems with giant planets in different masses, orbits, and they may have very different compositions of these planets. Earth-like planets can be very similar or very different from our own. Earth-like planets can form with low water contents or with very high water contents, possibly being water worlds or desert worlds, as Sean mentioned at the beginning. And giant planet dynamics drastically affect the growth of terrestrial planets, and they are almost always negative effects. If you have very few or very small giant planets in the system, you will have very large and very water-rich terrestrial planets forming in that system. While if giant planets reside in or near the habitable zone for long periods of time, you will have a very low probability of having a habitable planet. And now, using these factors, we can hope to begin to predict the nature and habitability of extrasolar terrestrial planets, hopefully useful for future missions. However, we have to really improve these models to truly understand the diversity of habitable planets in different systems. And these are all the different ways that models hopefully will be improved in the coming years. And we're reaching for this final point, number 4, a holistic planet formation model, which is core accretion of both terrestrial and giant planets with accurate water transport and destruction and formation of water-rich bodies in the system, and hopefully we can predict the frequency and diversity of planetary systems in different environments. So if you have more questions, you can contact Sean or me at our different emails. The other collaborator on the recent research was Stein Sigurdsson, my advisor at Penn State. You can also check out Sean's website and read the different papers that we've noted in this presentation. So we'll leave it open to questions that we have time for now at the end, and I guess we'll give the ball over to Marco over at headquarters.
Does anyone have any questions?
How are we doing questions? Are we doing them locally first or what?
Yeah, go ahead. Do the local questions.
Okay. Go for it, Nick.
It seems like the death sentence that you give to desert worlds comes from the assumption that all water comes from asteroids. So I was hoping to see cometary water as one of your future additions to the model.
Yeah.
Well, you have reasons for thinking it's not the most important. It probably does become the most important worlds if asteroidal water is not available.
Oh, I agree. We're actually looking at this at the moment with Nate Cave at the University of Washington. We're in the process of looking at that as well. I guess we didn't specifically mention it, but that's key to the puzzle as well. In some cases, cometary water might be the dominant source. But, good job.
Now, question for Avi. What was the gas-to-dust ratio in the simulations that you showed, and how does the outcome depend upon that ratio?
Well, in the last simulations, we start with a certain amount of solid material, basically about between 15 and 20 Earth masses of material total in the system, and this could be said to be using a general gas-to-dust ratio of about 0.1 or 0.01 with the star, 0.01 for about 100 for a gas-to-dust ratio, which is, if you assume 0.01, 1/100th of the mass of the star for the total mass of the disk, and 100 for the gas-to-dust ratio, you get about 15 to 20 Earth masses of material in the system. Now, the way that the gas-to-dust ratio could affect the final results would basically be in how much mass you'd begin with at the beginning and how quickly bodies would form in the system. As Sean mentioned at the beginning, there's a lot of uncertainty in how kilometer-sized bodies, how planetesimals form, and how that process is contingent on the gas-to-dust ratio pretty uncertain. We're hopefully going to be exploring a little more of these factors as we bring the simulations a little earlier in the formation process to smaller bodies, many more smaller bodies in the gas disk. But you're right that the gas-to-dust ratio will affect both the rapidity and size of the formation of bodies, and also the effectiveness of gas drag on those bodies.
A quick follow-up. Do you remove the gas instantaneously at a certain time, or is there a declining gas-to-dust ratio in the models?
There's a declining gas-to-solid ratio. So there's a declining gas-to-dust ratio. What we do is we start with a certain amount of solid material, and we do not add particles over time. So we assume that the majority of large bodies were formed by the start of our simulation. So additional planetesimals are not being added to the simulation, while the gas mass is decreasing from the beginning of the simulation till it disappears completely at 10 million years. So in that sense, the gas-to-dust ratio, or the gas-to-solid ratio, declines to 0 by 10 million years.
Fran?
Your conclusions were that you're better off without gas giants, and you seem to like 1 or maybe 2, but we have 4. So how do you prevent making gas giants?
Well, I mean, all right, that's a big question. So, did everyone hear the question okay? All right, I'll assume everyone heard the question. So, basically, what we were saying was that gas giants are usually a bad influence on terrestrial planet formation. They sweep up material, they chuck a lot of material out. They don't end up actually delivering much water. They don't really help the water delivery process at all. They just screw everything up. And our plot that we showed on which giant planet orbits allow terrestrial planets to form is not which giant planet orbit, which giant planets can smile and say, hey, terrestrial planets, everything's happy. It's which ones don't screw everything up so that terrestrial planets can be there. So the trick is how many systems actually have giant planets to start with. There's an interesting new observation suggesting that the population of known debris disks, where you have rocky material accreting in some sense, is actually anti-correlated with the known giant planet systems. So there are lots of systems out there where rocky things are colliding, but there's no giant planets. And it's hard to put a number on it right now, but it might turn out that a large fraction, maybe the majority of planet systems have no Jupiter-sized giant planets, or at least no inner currently detectable, Jupiter-sized planets. So
how do you do that? You don't have ice, or you don't have gas, or timing? How do you?
Yeah, there's lots of possibilities. I mean, depending who you talk to, giant planets are either very easy to form or very hard to form. And so the reason this would happen, maybe the disk dissipates too quickly, maybe the gas has gone too fast for runaway gas accretion to happen, maybe the amount of solid material is lower, maybe the time scale is simply too long for these things to grow to a given point, or maybe it's too hot, right? So there's lots of ways that you can do that. Or maybe they form and are destroyed. That's also possible.
If I could add to that, the formation scenarios for giant planets suggest that you need to get to a certain critical point, a critical mass, or a critical cooling rate. Actually, since we don't run simulations on giant planet formation, we can't comment in detail on this, but the idea is that you need to have a critical point where a gas giant will either have a critical runaway gas accretion or a gravitational collapse. Now, you could have, if you have either a small amount of gas or a rapid evacuation of the gas in the system, in high mass systems, you could have solid bodies forming without the actual processes needed to form gas giants. And so you could have a whole bunch, basically a whole bunch of small bodies that none of them have reached the critical parameters needed to form gas giants. And so it's, as Sean said, depending on who you talk to, you get different understanding of how important each parameter is, but there are various scenarios where you could end up with lots of small bodies in the system and either none or very small gas giants. So.
We have a question from NASA Ames.
Hi, yeah, this is Dave DeMarais here. I have a question about a process or a role of giant planets that seems like it's related to your discussion, and that is this role of a shepherd. The idea that having a giant planet somewhere in the system will capture a lot of asteroids and so forth and avoid impacts on Earth-like planet. In the case of where the giant planet is inside the orbit of a habitable planet, it would seem to me that that role would not be as effective, but is it still something that would be important? In other words, would a giant planet just inboard of a terrestrial habitable planet have any kind of a protection role with respect to asteroid impacts and stuff?
All right, let me answer this one, or I'll start off. So the idea that Jupiter is a great protector for the Earth is not as well established as some might think, because the comets that Jupiter protects us from would not be on those orbits if Jupiter hadn't put them on those orbits. So it's somewhat circular. And it's not that Jupiter isn't protecting us in some sense, but I haven't seen any papers which really address this properly. If you had a system where you had a planet in the habitable zone and then an inner giant planet, that giant planet would probably not do too much protecting of the planet in the habitable zone. In a few instances, you might have very high eccentricity comets, just miss the Earth-like planet, and then have a close encounter with the giant planet, and then end up getting scattered out. That could happen in a few cases, but I think in general it wouldn't be a big effect.
Okay, there's a question at Goddard.
Yeah, this is Mike Muma. The question really devolves around this issue of what do we mean by a comet and its role in delivering water to these Earth-like planets. First of all, we should probably call the bodies of interest icy planetesimals, which begs the question of whether they're the asteroids in the 4 to 5 AU region that you've been talking about, or the icy bodies further out, which presumably constituted the feedstock that let the cores of Jupiter and Saturn grow to a size where they could capture a nebular gas and grow to their present sizes. And the interesting issue then, the testable hypothesis, is whether there is a D to H ratio gradient in the water ice in those icy planetesimals as one goes from 4 AU to, say, 10 AU. Because this should then show up as a testable aspect of your model as to whether, in fact, the material scattered from the Jovian-Saturn region can, in fact, impact terrestrial planets in large abundance and deliver significant mass, as opposed to merely going out and populating the Oort cloud during its formation phase. So I think there are, in fact, many hidden assumptions in the present models that have been published about the role of icy bodies from the 5 to, let's say, 10 AU region and their contributions, which I would encourage you to explore in some detail.
Yeah, right. There's lots of uncertainty in terms of the DDH ratio of comets. As far as I know, it's only known for 3 comets, all of which are Oort cloud comets. And the formation location of those comets is quite uncertain. In addition, there's lots of uncertainty in terms of the D to H ratio evolution on the Earth. It might not have stayed constant over time. And these are things that need to be looked at in more detail. The general model, the general picture, as envisioned by this Morbidelli paper in 2000, suggests that the D to H ratio of water on the Earth is a nice match to the D to H ratio in carbonaceous chondrite meteorites, which have a source region of something like 3 AU or so. And so that's the general argument why asteroidal water, well, it's one of the arguments why asteroidal water might be favored. But there's other things which are obviously uncertain.
Well, I would respond to your comment first about D to H ratio of the 3 comets for which has been measured. Really only one of those 3 measurements is highly reliable, and that one is for Comet Halley. The other 2 comets are based on a single rotational line of HDO and water measured by a different instrument at a different time. This means that the line formation region in the coma is different for HDO and H2O, and therefore there's a tremendous extrapolation getting to a D to H ratio for that individual comet in the case of Hale-Bopp and also Hyakutake. So it may well be that the agreement amongst the three comets is coincidental. The second comment I would make is that millimeter infrared observations of parent volatiles, specifically organics, in recent comets, a dozen or so, have shown that there are at least two separate populations based on the organic chemistry. And the suggestion has been made that one population dominant in the Oort cloud was actually formed in the outer giant planets region, whereas the organic depleted fraction, the other population, was likely formed in the inner giant planet region. So in that case, if that's correct and holds water, it would mean that, again, you really couldn't use the measurements in those three comets of D to H to interpret what would have been delivered to Earth, because they would have been more characteristic of the population in the outer giant planets region, not the inner.
So what we need is someone to go and tell us the D to H ratio of all these comets then, eh?
That's exactly right.
All right. Well, I look forward to hearing the answer.
Can I zoom in? Also, I wanted to say something about water, period. Water in young planetary systems, the location and transport of water in young planetary systems is something that I think is one of the biggest controversies in planet formation, period, right now. I mean, our understanding of where water forms, where solid body water forms in the system and how that evolves is itself still evolving right now, because as we probe the temperature structure of disks and as we understand more about how passive and active circumstellar disks evolve over their lifetime, which is the critical point where planetesimals are being formed in the disk. It evolves, as we say, frost line evolves from the interior to the exterior to the interior and back again in the disk. And so understanding that evolution of the temperature structure and how that affects the formation of bodies in the disk. And then, as we said, understanding how that might affect the D to H ratio as solid water is formed in different parts of the disk on different bodies. I think we have a long way to go in this understanding of where the water came from on Earth and in other systems. So let's just put it that way.
University of Washington, do you have a question?
Yeah, so presumably your end result depends a lot on how quickly the giant planet migrates, which in turn is a function of the disk properties. So I was just wondering if you could talk in a little more detail about what the properties of your disk were, particularly sort of in relationship to our sort of canonical minimum mass solar nebula.
I'll start with that one. The disk, as you said, the disk properties were mostly related to the migration of the giant planet and then the effect of gas drag on the smaller bodies in the system. The migration of the giant planet was based on simulations of giant planet migration in hydrodynamic simulations, which is, as you know, is related mostly to the viscosity of the disk in hydro simulations. And however, if you assume an infall rate onto the star, that can give you a transport rate of the gas in the disk, and that can give you an inspiraling rate for the material. And the way the Type 2 migration works is that the giant planet is locked into the disk and then spirals inwards with the gas spiraling. And so hydrodynamic simulations of giant planet migration have shown that Type 2 migration is generally very robust between 100,000 to 1 million years for the migration rate for a giant planet. That can, if you have a very low mass disk, that can affect it, or if you have possibly a very high mass disk where the planet is is subject to other forces greater than type 2 migration, but we're assuming a general gap opening rate of about 100,000 years for type 2 migration of the giant planet. Other simulations have shown that you can have a variation in the scattering rate depending on the migration rate of the giant planet. We published a paper about 3 years ago showing that. But we're relying here on much more detailed hydrodynamic simulations to give us the rate of migration for type 2 migration. Now, for gas drag on the smaller bodies, that's much more uncertain. We assume, as you said, a basic gas-dust ratio of about 100, and that gives us a certain density for the initial density for the gas in different parts of the disk. We assume a certain surface density profile to go along with that, and so those are, as you could say, arbitrary choices that we make in our gas density, our gas parameters for the disk. And I think a lot more work needs to be done to understand the role of a less dense or more dense or different surface density profiles on the delivery of water to habitable planets. However, since we don't know that much about the we're not including that much about the evolution of water ice creation in the disk. I think we have other parameters that need to be refined as well as those for us to better understand the water transport. So in these first simulations, we have assumed intermediate values for the gas disk and the water content in the disk, but that can be modified to explore more parameter space. So
we have a question from Penn State.
Hi, Sean and Avi. It's Jim Casting. Actually, Avi, your last response, can you hear me?
Yes.
Your last response sort of sets up my question. If I understood you correctly, you assume 100% retention of water on these growing planetesimals. What do you think the actual percentage of water retention should be for Earth or for a planet in general?
There's lots of stuff that goes into that. Oh, are you going or should I go? I'll do it. All right.
You go, Sean.
So there's lots of details that go into there. As you know, there's during big collisions, there's probably a decent amount of water loss. And there's some new simulations by Robin Canup and Betty Pirazzo saying, with a few different impact parameters and impact speeds showing that maybe half or so of the water should be retained in giant impacts. So over the course of the formation of a planet like the Earth, I mean, a hand-wavy number is something like, a quarter or maybe as low as 10% of the total water probably ends up on the surface of the planet. There's lots of unknowns in there. The reason that, our key thing that we were saying that in hot Jupiter systems, terrestrial planets that form probably have lots of water. The reason we think that is because we're not comparing those to the Earth. We're comparing those to other simulations with the similar assumptions that were designed to reproduce the Earth. And so we think that conclusion is pretty robust. Those simulations that were designed to reproduce the Earth tend to have too much water by maybe a factor of 5 or 10. And so that's kind of a very hand-wavy number to give in terms of how much water depletion occurs.
Maybe that's a good thing, right?
Okay, we have a question from Goddard Space Flight Center.
Okay, the question is, you were saying that planets form as, planetesimals at 0.1 AU. Some of them are reaching water. How stable is water there? Normally the delivery you were saying is kind of fast. It's at the beginning of the simulation.
Yes.
So how stable is this water? You deliver there and...
I might as well take it. At the beginning of the simulation, the planetesimals at 0.1 are in the interior part of the disk have very or no water, basically. And then the water is delivered through radial migration, and you end up with bodies that have some amount of water. And you're correct that we don't include any loss of water in bodies that are formed in these simulations. So we don't include evaporation. We don't include destruction through collisions. So in the interior part of the system, if the water is on the surface, it will be quickly evaporated away. If there's not a thick steam atmosphere, which maybe more of the atmospheric scientists could tell us a little more about the the retention of water under a dense atmosphere. But we don't include any loss of water in these simulations. And so you would have to have a more detailed evolution of the say, super Earth at close distances. But you could have a much smaller mass of the actual planet than we would find in our simulations at small distances, because of if a large fraction of the material is volatiles and that is lost through evaporation, possibly planets that you discovered now would be much smaller than might have originally occurred during the formation process. So you're right, that's something else to take into account.
We have a question from Mark Clare. Mark, are you there?
Hi, Sean and Avi. This is Mark from UW. The title of your talk was, "Are We Normal?" So I guess I was wondering about our solar system and what your simulations might show as to that fact. We had a lot of gas. We formed these large gas giants, but they did not migrate into the inner solar system. What constraints does that place on how planets formed in our own solar system, and whether or not that might be a normal outcome of simulations like yours?
Sean, me, what do you want to do?
We'll have to reconnect
Sean's
to
not
see
responding.
you. Just one moment.
Oh,
So if you
okay. The question of how common our system would be versus other systems which have a close-in giant planet, I think, is reserved for more detailed simulations of a variety of disk parameters with giant planet migration included in it. What we tried to do in our simulations was show, under a variety of these conditions, if you had giant planets in a variety of orientations, whether you could form planets that were like Earth or not like Earth, and how similar the final characteristics might be to our own Earth.
Yeah, that's a good question. The trick is no one knows how migration stops. And so most people think that planets do migrate. And how do they stop? Some people think that maybe the disk is dissipating. And so once the mass in the disk is less...
lost him again.
Yeah. I might as well finish what Sean was saying. Sean was saying as the mass is dissipating in the disk, you end up with the planet not having enough material exterior to the planet during migration to continue to force it inwards, and so the planets can stop migrating through that process. Other people believe that our system would be even more unusual than other systems because Jupiter and Saturn formed close together, relatively, within 4 AU of each other. And if planets, some simulations show that planets within that form close to each other evacuate the gas mass between them, and this may halt migration for the interior planet. Hopefully Sean can check in when he gets back on. But
oh, it's okay.
As he said,
I can ask Sean later.
Okay, all right.
All right, we just got back again. Can you guys hear me?
Sean, yeah. I kind of completed your statement about the different ways that migration could halt, but
that works.
Hi, this is Carl. I thought I'd break in before the technical glitches end us abruptly, and just thank our speakers again. And I'd also like to thank all the participants and particularly all the folks who asked questions. I'm kind of new to this format, and I'm thrilled, frankly, with the amount of interaction that we've had, both the talk and then the last half hour of Q&A. So thanks once again to both Avi and Sean. Thanks to Goddard for hosting Avi there, and I don't think I mentioned that in my introduction. And thanks to everybody who participated. We will not have a director seminar in December because of the holidays, so the next director seminar will be in January. We'll be sending out a note about that, and the speakers there, I believe, are going to be Lisa Pratt and T.C. Onstadt, and they're going to be talking about the deep biosphere work that has been done by the Indiana, Princeton, and Tennessee team. So thanks again to everybody, and we'll see you all in January.